Hello, hi there. Today we are going to look at the second part of persistent homology. Okay, and the first part of persistent homology, the introduction of how we can quantify shapes. Okay, so that would be the second subtopic of what we did in previous lecture. Shape quantification with topological invariance. Okay, so in this section, we looked at two types of quantification. The first type would be Euler characteristics, and the second part was on Betti numbers. So if you look at Betti numbers, are in fact the alternating sum of Euler numbers. Okay, and then of course, if given a collection of point cloud, we would want to quantify so-called the nth dimensional whole of the point cloud, which is using Betti numbers. But in the process, we have to build a out of the point cloud such a way that we would be able to compute the Betti numbers. The computation of the Betti numbers and nth dimensional whole, it's called homology computation. Okay, so the first part of analysis was on mapper algorithm. We input point cloud, we get a structure of the graph, which is in one-dimensional skeleton called graph. Yeah, the graph would be a collection of vertices, edges, right? So this is a graph. And what we are trying to do today is that to understand how we can input the point cloud and get the information of the shape in the form of persistent homology, in which we would get a nice plot called persistence diagram. Okay, on our left-hand side here. So here on the left-hand side, we can see the information of zeroth Betti number and information of H1 or one-dimensional whole Betti numbers. Okay, so on the left-hand side here. So the x-axis represents the birth, the nth dimensional whole, whereas the y-axis represents the death of that whole. Okay, so we here in this diagram, we encode connected components, which represents H0 in red, and also the blue points represents H1, which is one-dimensional wholes of Betti numbers. Okay, let's look at an example to understand further. Okay, now if you see, I have actually given a link in your PowerPoint where you can download this Mathematica code and play with it. Okay, so first we have a collection of points in two-dimensional points. And this is a two-dimensional point, so-called a toy data set, in which we are going to use for this simulation. Okay, so just a collection of two-dimensional points, right? And we are going to create a filtration. Filtration means we're going to create a simplicity complex at various resolution using so-called a ball. Okay, and then by so-called introducing a simple condition to create a simplicity complex, we would then compute the Betti numbers. Okay, so let's look at an example. So in this example, you can see that at each point, At each point, there is a ball. The ball is the cover for that point. As we increase the size of the ball, we see the ball is intersecting among each other. When a ball intersects, for example, at this point here, then we draw an edge. Okay, so the edge is now connected. We have the edge. Now we have two edges. Right, so as we increase the size, the connection of edges means, so this is now, these 2 points becomes one connected component. So the connected components means the number of connected component decreases edge. Okay, so now I see at this level now, there is here, if you look at these 3 points, it connects and quickly shuts the triangle. Yeah, the right triangle was given birth, and then quickly it dies, right? So there is one radius giving birth, which is a birth number, and another radius giving the death number. So we can just keep on increasing and keep building complex and keep track of the changes of H0, which represents a connected component, and H1, which represents one-dimensional whole. Okay, so just keep building this implicit complex. 0.338, radius 0.338, we have the birth of two holes. Yeah, so we have to keep track of each hole actually. So the first one, the small hole here, and then the big hole. And then as the hole persisting, still the two holes are persisting, still the two holes are persisting. At 0.416, we have the death of the small hole. The death simply means the hole has now been closed, right? Now we can keep increasing. So the big hole still persisting over the radius, keep on increasing, and keep on computing the, keep on keeping track. Okay, all right. So now 0.8, so roughly 0.8, that the depth of the big hole can be seen clearly, right? So this is how actually we keep track of the birth and death of each so-called feature. Here the feature either H0, which represents connected component, zeroth dimensional whole, or H1, which represents one dimensional whole.